In this lesson, we are going to talk about polar arc length. I'm going to derive that formula for you. And then we're going to review some parametric and polar facts, and we'll talk about particle motion. Okay. So, in order to get the polar arc length formula, we're going to start with an arc length formula that we derived a couple of weeks ago, and that would be the parametric arc length formula. Okay, so in parametrics, the arc length formula is the integral from a to b of the square root of dx dt squared plus dy dt squared dt. Okay. So let's rewrite this in polar variables, and then from there we'll be able to completely transform it. So let's say that we're going to let x equal r cosine theta, and we're going to let y equal r sine theta. And we're going to say that our r function is some r is some function of theta. R is some function of theta, which means that x is f of theta cosine theta, and y is f of theta sine theta. So I have a set of parametric equations here where x and y are both defined in terms of theta, so theta is my parameter. So I can think of, if I think of theta as my parameter, this parametric form of the arc length equation could also be written as the integral from alpha to beta of, instead of using t, I'm going to use theta. So dx d theta squared plus dy d theta squared. And d theta. But if we want a polar version of this equation, then our formula needs to be in terms of r's and thetas, not x's and y's and thetas. So now we're going to do some work to get rid of the x's and y's and only have r's and thetas. All right, so we have an equation for x and for y, and I'm going to take the derivative of those because I need a dx d theta and I need a dy d theta. So dx d theta, I'll put this over here, dx d theta, and now I have to use the product rule because I have a product of two functions here, is f of theta times negative sine theta. So that's negative f of theta sine theta plus f prime of theta cosine theta. Okay, and now I'm going to do the same thing for y. dy d theta is, again, the product rule is going to give me cosine theta, f of theta, plus f prime of theta sine theta. Okay, so now let's take a look at our arc length formula. I have dx d theta and dy d theta, and they're both squared. So I'm going to now square both of these. So dx d theta squared. So I'm going to need to FOIL this squared expression. Okay? So I'm going to get negative f of theta sine theta times negative f of theta sine theta, which is going to give me positive f of theta sine theta squared. And then I'm going to get, let's see, minus f of theta, f prime of theta, sine theta, cosine theta, and then minus another of the same. So my OI in FOIL is going to give me minus 2 f of theta, f prime of theta, sine theta, cosine theta. And then my last term is going to give me this squared. So f prime of theta cosine theta squared. Okay, so let's go and do the same thing for dy d theta. When I square that, I'm going to get f of theta cosine of theta squared. And now I'm going to get plus f prime sine cosine plus f prime sine cosine. So plus 2 f of theta, f prime of theta, sine theta, cosine theta. And then at the end, I'm going to get f prime sine theta squared. F prime of theta, sine of theta squared. All right, well, now we're going to do some linear combination. We want to add these two together because what we're really going for is dx d theta squared plus dy d theta squared. So when we add the left sides, we get what's under the radical here, dx d theta squared plus dy d theta squared. And when we add the right sides, well, the middle terms are going to cancel each other out because I have a minus 2 and a plus 2 of the same expression. And then here, I have f of theta squared sine squared theta plus f of theta squared cosine squared theta. Well, if I factor out the f of theta squared, I'm going to have a sine squared plus cosine squared, which is 1. And so I wind up with f of theta squared. And over here, the same thing. I square and add them together and then use the Pythagorean property to make cosine squared plus sine squared 1, and I wind up with f prime of theta squared. Okay, so now we're going to now take this nice simplified expression we just got and plug it back into this parametric form of the formula for arc length. And so I'm going to get, so arc length equals the integral from alpha to beta of the square root of f of theta squared plus f prime of theta squared. Oops, sorry, that should be out there, squared. Okay, d theta. But remember back here, we said, what is f of theta? F of theta is r. So this is really the integral from alpha to beta of r squared plus, well, r prime. If r is a function of theta, then the derivative of r is dr d theta squared. That's f prime of theta squared d theta. And this is the formula for arc length in terms of r and theta in polar variables. All right, great. Now let's use that formula to find the area of a curve. Okay. So let's find the area, the length of the cardioid, 1 plus cosine theta. Okay, we'll leave our formula up there. Find the length of the cardioid, r equals 1 plus cosine theta. So hopefully you know what that looks like, but let's draw a picture. So I'm going to just do the critical values and the nice family. The nice family, easy points to plot for cosine would be pi over 3. Okay, so the cosine of 0 is 1, so we have 2, 0. R theta is 2, 0. The cosine of pi over 2 is 0, so we have 1 pi over 2. The cosine of pi is negative 1, so that gives us 0 pi. maybe at this point you realize there's symmetry. The cosine of 3 pi over 2 is 0, so we're going to get 1 3 pi over 2. Oh, I don't think this is very symmetric. I think this should be higher up. Yeah, maybe over there. Let's ignore it. Let's pretend that one's not there. Put this up here a little. Okay, and then we're back to 2 pi. So now I'll just throw in a couple of more points just to make it a little bit prettier. Make sure I get the shape well. There, now it's gone. So the cosine of pi over 3 is half. So I'm going to get 1 plus a half, or 1 and a half at pi over 3, so maybe about there. And I'm going to have a symmetric point down here. Okay, so we're going to have a nice cardioid now. There it is. And what's really important to pay attention to is the angles. As I drew the cardioid, we had to go all the way from 0 to 2 pi to draw the whole cardioid. Okay, so that I need to know that because that's going to help me set up my limits of integration. So there's several ways you could do this. You could do 0 to 2 pi. You could also do 2 times 0 to pi, because that would give you the first half. So that would give me the curve up to this point, and then you multiply it by 2 because of symmetry to get the length of the entire cardioid. I don't think it's easier to plug in one set of limits for the other, so I don't think that that really would matter in this particular problem. Okay, so we have the square root of r squared. So this is going to be so this is going to be, maybe I'm going to do a little bit of side work here before I write out my integral. So r squared is 1 plus 2 cosine theta plus cosine squared theta. And then I need dr d theta. So dr d theta is going to be 0 minus sine theta. And then squared is sine squared theta. So now, if you see, if I add r squared plus dr d theta squared, I'm going to get 1 plus 2 cosine theta plus cosine squared plus sine squared. Cosine squared plus sine squared is 1 plus that 1. So this is going to be 2. That gives me 1 plus 1 is 2 plus 2 cosine theta d theta. And we can just go ahead and type that into the calculator. So we could either do the integral from 0 to 2 pi, or we could do 2, the integral from 0 to pi, 2 plus 2 cosine theta. These are equivalent. These will give equivalent answers. And let's go ahead and type that into the calculator. So I'm going to make sure I'm in radians. Yes, I am. Math 9. Okay, so the integral of the square root of 2 plus 2 cosine theta from 0 to 2 pi. Let me just double check it. Looks good. Look at that. Exactly 8. Exactly 8. The length of that curve is 8. I would call that arc length equals 8. I would call that mathgical. 8. Exactly 8. Okay. All right, so that is a nice intro to polar arc length. Okay. And now we're going to talk about particle motion. Actually, you know what? Now we're going to review some, before I talk about particle motion, let's just review some important parametric and polar facts. Okay, so let's start with some parametric facts. So parametric facts that are going to be important to us. Let's see. And these are things you should have memorized. Parametric facts. The first one is when you have a parameterized curve, how do you find the derivative? How do you find dy dx? And that is going to be dy dt over dx dt. And then from that, how do you find the second derivative? Well, the second derivative is the second derivative, well, that's going to equal the derivative with respect to x of the first derivative, right? And so that is the, I'll write that in one other way, the derivative with respect to t of dy dx, that's the derivative of the original derivative divided by dx dt. So just a note there, whenever you take the second derivative, make sure you're using the original dx dt, because sometimes you can simplify this, you can reduce the fraction. Don't use a simplified version of your denominator, because that might not be your original dx dt. Always use your original dx dt when you're finding the second derivative. And then we just reviewed it, but I'll put it up here again. Parametric arc length is the integral from t equals a to t equals b of the square root of dx dt squared plus dy dt squared dt. Okay. Important polar facts. So let's just start with the very basic stuff. You remember from pre-calculus, all of our polar relationships come from this picture where we're relating, trying to relate an ordered pair x and y to that same point represented as r and theta. Okay, so x is our cosine theta, y is our sine theta, the tangent of theta is y over x, and then of course we have the Pythagorean relationship, r squared is x squared plus y squared. Okay, those are all facts you knew from pre-calculus, and this year we've also taught you polar area. Polar area is the integral from alpha to beta of 1/2 r squared d theta. So you can see that the variable of integration here is theta, so you would write your r value as some function of theta. And then we just taught you polar arc length, so that's going to be the integral from alpha to beta of the square root of r squared plus dr d theta squared d theta. Okay, so the last thing I'm going to cover before we do a few AP problems is particle motion. So let's talk for a second about particle motion and how derivatives, parametric or polar derivatives, tell us about different types of particle motion. All right, so first of all, when is a particle at rest? Okay, so let's... Okay, so when is a particle at rest? Well, if we have a particle moving along a parameterized curve, if it is at rest, then it can't have motion in any direction. So therefore, a particle motion. So a particle is at rest when dx dt equals 0 and dy dt equals 0 for the same t value at the same time, that means. Okay? So what kind of a motion does a particle have? So let's look at different kinds. So first of all, let's say dx dt is positive and x is positive. So the derivative of x is changing in the positive direction, and x is already positive. So you can imagine that if this is the y-axis, you've got a point somewhere over here, and the point is moving this way. So this is moving away from the y-axis. If dx dt is positive, oops, I need a 0 there, and x is negative, well then we've got a point on the other side of the y-axis, but it's moving in the positive x direction, so in this case the particle is moving towards the y-axis. Okay? All right. I can write out similar things for motion up and down. I'll just really quickly, if dy dt, okay, let's look at the other possibility. Let's look at if the derivative is negative for y. So if the derivative is negative and y is positive, or y is negative. Okay, so the derivative is negative. So the particle is moving in the negative y direction, but y is positive, so the point is above the x-axis. But moving in the negative y direction, well, in this case, the point is moving towards the x-axis. And if the derivative is negative and y is already negative, so that means y is already below the x-axis, the particle is already below the x-axis and moving in the negative y direction, then the particle is moving away from the x-axis. And of course, there's another set where dx dt is negative or dy dt is positive, but you can just draw yourself a little picture, and it's easy to logically figure out what is a particle moving away from or towards. And lastly, I'll just talk about, movement in polar. If dr d theta, oops, I'm running out of room here. Dr d theta is negative. That means the radius is getting smaller. Well, if the radius is getting smaller, then you're moving towards the origin. And of course, if dr d theta is positive, the radius is getting bigger, then the particle would be moving away from the origin. Okay? Okay, so that's particle motion. And then we are just going to do some sample AP problems. So hopefully you have printed out the examples handout, and we are going to run through those problems together. And they will help you do some other homework problems. Okay, So, print out the examples handout. Here's problem number 1. A particle with non-zero velocity is moving along the polar curve r equals 4 minus 2 cosine theta and has position x of t, y of t when at time t with theta equals 0 when t is 0. Okay, so the particle is moving along the curve so that dr dt is dr d theta. Find the value of dr dt when theta is 5 pi over 3 and interpret your answer in terms of the motion of the particle. Okay, so we are trying to find dr dt, so I need to take the derivative of the r function. So dr d theta is, well, this is going to be 0 minus 2 times negative sine theta sorry. We're taking the derivative with respect to t. Sorry about that. Okay. So no. Okay, let me back this up a second. Dr d theta, the derivative with respect to theta is negative 2 negative sine theta, d theta. But they told us in the problem that dr d theta is equal to dr dt. So dr dt is 2 sine theta. And we are trying to evaluate dr d theta when theta is 5 pi over 3. So I am plugging that in to my function. The sine of 5 pi over 3 is negative root 3 over 2. So dr dt is negative root 3. Okay. So interpret my answer in terms of the motion of the particle. So let's think about the particle motion relationships we just talked about a moment ago. I'm going to say that dr d theta is negative. Therefore, the radius is getting smaller. So the particle is moving away from the origin. Oh, sorry. The radius is getting smaller. Let's back that up. The particle is moving towards the origin. Okay, great. All right, next question. Yep, we are all set there. A particle is moving along the same polar curve. The particle moves so that dy dt is dy d theta. Find dy dt when theta is 4 pi over 3. Well, you don't really see a y in the equation. So hopefully you see this done once and you'll remember what you need to do here. So we want to think about our polar Cartesian relationships, because y is a Cartesian variable. And if you think back to those polar facts that I wrote out a little while ago, we know that y is r sine theta. So we can write an equation for y of theta by plugging in our r function, 4 minus 2 cosine theta sine theta. So you could do the product rule, or you could multiply this out. I think I'm going to multiply it out. So let's make this 4 sine theta, and then minus 2 sine theta cosine theta, which is just sine 2 theta. Okay, so dy d theta is 4 cosine theta minus, this is going to be 2 cosine 2 theta. And they've already told us that dy d theta equals dy dt. And now we are trying to find dy dt when theta equals 4 pi over 3. So that's going to be 4 times the cosine of 4 pi over 3 is negative 1/2 minus 2. I'm going to put that 4 pi over 3 in there, and I'm going to get the cosine of 8 pi over 3, which is the same place as 2 pi over 3, which is also negative 1/2. And I'm going to have negative 2 plus 1, which is negative 1. Okay, so I know that dy dt is negative 1. So to interpret my motion, I need both a dy dt and a y value. I need to know if y is positive or negative. So remember that y is r sine theta, and so I can, or 4 minus 2 cosine theta sine theta. So y at 4 pi over 3 is going to be 4 minus the cosine of 4 pi over 3, we already said, is negative 1/2. So this is going to be 4 minus 2 times negative 1/2, which is 4 plus 1. 4 plus 1 times the sine of 4 pi over 3, and the sine of 4 pi over 3 is negative root 3 over 2. So this is negative 5 root 3 over 2. So think about those particle motion relationships I talked about. Dy dt is negative, and y is negative. So y is somewhere below the x-axis and moving in this direction. Therefore, the particle is moving away from the x-axis. Okay. Okay, second page of examples. Same function. We're still working with the same function. There is a point on this polar curve, this limacon, where the y-coordinate is 1. Find the angle that corresponds to that point. Okay, now, you could visually just see this, and we're going to figure out what the angle is. But first of all, we're looking in this section, because it says somewhere between 0 and pi over 2. And you can see y is 1 would correspond to this line. So we're looking for a point over here. That's going to be the point we're looking for. Okay, so we already said that y is r cosine theta. And so we want y to equal 1. 1 is 4 minus 2 cosine theta. Oh, sorry, I wrote that incorrectly. Y is r sine theta. Okay, good, we didn't get too far here. So we're going to use a calculator for this. We don't really need to do any simplifying. Let's just move everything over to one side. So we're going to have 4, maybe I'll multiply this out, 4 sine theta minus, remember that's sine 2 theta. And then I'm going to subtract the 1 over to the other side. And now I'm going to get my handy calculator out. And I'm just going to find the 0 on this equation. Now, my answer is going to be in radians. It's going to be somewhere between 0 and pi over 2, somewhere between 0 and pi over 2 is about 1.5. So I'm going to use the graph. You can use the equation solver. There's several ways you can do that, but I'm going to use just the graph. So I'm typing in 4 sine x. I'm just using the function mode of the calculator, minus sine 2x minus 1. And then remember, my window, I'm finding a theta between 0 and, well, I can just put pi over 2. And I just need to see the x-axis. So I can set that from -1 to 1. And There it is. You can see it's a little bit past 0, which is what we were expecting. I'm going to use the calculate the 0, second calculate number 2, 0, and my left bound is 0, and I'll put my right bound as 1. And there it is. The angle where y is 1 on that polar curve is 0.4683 radians. So theta is 0.4683 radians. Okay? So you could also use the equation solver, whatever you prefer, whatever method you prefer there. Okay, last problem for the lesson. Okay, still on the same curve, the same limacon. A particle is traveling along the limacon, along the curve r equals 4 minus 2 cosine theta. And we're going to find dx dt when theta is 2 pi over 3 and interpret the meaning of our answer in the context of the problem. Like what is the motion of the particle? So this is very similar to the problem on the other side. You might want to pause the video, do the problem on your own, and then come back and look at my answer and make sure we match. Okay, so x, just like we used y equals r sine theta, x is r cosine theta. So x of theta is 4 minus 2 cosine theta. That's our r value, cosine theta. Okay, so I'm going to multiply. Am I going to multiply it out? Yeah, I think I am going to multiply it out before I take the derivative. 4 cosine theta minus 2 cosine squared theta. All right, now I'm going to take the derivative, dx d theta, which we've been dx d theta. Oh, no, sorry. Now, tricky problem here. Let's pay attention. Not paying attention here. We are not given the relationship that dx d theta equals dx dt. So we have to find. We're going to take the derivative with respect to time. So dx dt. So we're implicitly differentiating with respect to time. So this is going to be 4 sine theta. Oops, sorry, negative 4 sine theta d theta dt. That's why they gave you this piece of information over here. And then I'm going to have plus 4 cosine theta sine theta d theta dt. Okay. So now we're going to find dx dt when theta is 2 pi over 3. So that's going to be negative 4. The sine of 2 pi over 3 is root 3 over 2. D theta dt is 2, given in the problem, plus 4. The cosine of 2 pi over 3 is negative 1/2. The sine of 2 pi over 3, we already said, is root 3 over 2, and d theta dt is 2. So that is going to give me negative 4 pi over 3. Oh, sorry, 4 root 3. What am I talking about? And then I'm going to have minus, and this is going to be a 2 root 3, giving me negative 6 root 3. So we have that dx dt is negative 6 root 3. To make a statement about motion, we need to know what dx dt is, and we also need to know what x is at that moment. So x of 2 pi over 3, I'm now plugging into this equation up here, is going to be 4 times the cosine of 2 pi over 3, which is negative 1/2, minus 2 times negative 1/2 squared. So this is negative 2 minus 2 over 4, so minus 1/2, which is negative 5/2. So I have that dx dt is negative and x is negative. So let's draw a picture of that. So that means that x is somewhere over here on the left side of the y-axis, and it is moving in the negative x direction. So the particle is moving away from the y-axis. Oh, wow. Okay, that was a big lesson, and I hope I managed to cover everything. Yep, we went through polar arc length. We talked about parametric and polar facts. We talked about particle motion, and then we did some practice AP problems to prepare you for your homework AP problems. All right.